right, so on the first day of class, we had practiced telling whether compounds were soluble in H2O or not. And we said that our covalent compounds, it kind of depended whether it was polar or non-polar covalent. But we said that our ionic compounds were usually soluble in H2O. Well, this is where we get to talk about the fact that it should be, yes, all of them should dissolve, but that's not necessarily always the case. So, ionic compounds aren't all soluble in water, and all we're going to need to be able to do in order to tell which ones dissolve in water or not is look at the back of our periodic table. So I'll actually come back to this chart, or these notes on our packet on page 8 here in just a moment. We're actually going to be taking most of our notes here on the back of our periodic table. So the part of the back of the periodic table that we're going to be focused on is this center section. We've already talked about that polyatomic ion list in our activity series. That's not what we're focused on here. The rest of that middle chunk of our periodic table on the back is all about the solubility of our ionic compounds. And it's pretty simple. It's broken up into two parts. You can already see that line there. And that top part is a section describing where our compounds are soluble, and the bottom half describes where they are insoluble. So all of these ions that are part of our ionic compounds are things that tend to either be soluble or insoluble. So if I see any of these elements and ions in any compounds, then for the most part, those are going to be soluble compounds. If any of these things are in any compounds, then that compound is probably an insoluble compound. And that's the simplest way to look at it. That's most of what we do with this chart. Like you see, though, there is kind of a second section on the right where we have some exceptions. And so in that top part, if we're talking about exceptions to our soluble rule, then these are things that are going to cause those soluble ions to become insoluble. And I would recommend that you write that out just so that you can see it in front of your face. It's hard to kind of remember that's what that means there unless you see that word. And the more you practice, the less you might need it. But especially since this is the first time we're doing it, this is really all the notes we'll be taking about how to use our periodic table. And down there in the insoluble section, the bottom half, if I have exceptions to my insoluble rule, then those exceptions are going to be making my compounds soluble. So that's really all of the notes that we need to write on it. And the way that we use it, if I had a compound like NaNO3, then we're always going to be looking at the second kind of part of the compound, so the NO3 part. And the only reason that is because almost all of these ions in our list are negative ions, and negative ions are always at the end of our compounds. So it might seem backwards, but we're going to be working our way backwards to the front of our compound when we look at solubility. So NO3 is here in our soluble list. So I'm pretty sure that's going to be soluble, but we always have to check if the first element, the thing with that negative ion, is on the list of exceptions, because anything that we have written over here are ions that can make these ions insoluble. So luckily for NO3, there's nothing that will make it insoluble. It is always, always, always soluble. But if instead I had an Na written over here, that Na with my NO3 would pull my compound over into the insoluble area. So we just start from the end and work our way up front. We always look at the last ion first and then check the exceptions to see if that first ion, the first part of our formula, is there. So that's really what we're going to be doing for the most part. I do want to talk a little bit about these exceptions at the bottom in the insoluble area. Well, I guess it's the exceptions that make us soluble, because it looks a lot pretty repetitive here. If you notice, NH4 is an exception to every single ion that's insoluble. So no matter what it's with, NH4 is soluble, no matter what. And in fact, that's such an important thing to remember and realize. NH4 is the only positive ion that's in our solubility chart. So it is up here, but a lot of people don't remember to use that, and they don't really have to, because even if you start from the end, like you always do, no matter what that ends with, even if it looks insoluble, that NH4 is always going to be in that exception list, reminding us that it is always going to be soluble. Now, the thing I really do need to draw your attention to, that just like that NH4, every single thing that is insoluble can be made soluble if it's connected to the alkali metal cations. And it would be a lot more helpful if they would list out and remind us what those are, because part of my brain kind of remembers alkali metals from some point in time, but I don't really remember what they are or where they are. I'm sure they're on the periodic table someplace. If you did forget, like it's so easy to do, our alkali metals are the first column of metals. So everything in the first column except for hydrogen. And I might recommend that you make a quick note of these, or kind of remind you what they are, so that we can read down that list and we can see this reminder. And you have a little bit more space than I do at the bottom, kind of underneath this section. So maybe just highlight all of these words in the same color and then list them out right next to it. So going down the list, Li, Na, K, Rb, Cs, and Fr. So if I see any of those in a compound, no matter what it's with, those are going to be soluble. So always, always, always going to be soluble if we have an alkali metal or NH4. And you don't have to memorize that. It's always waiting for you here on the back of our periodic table. I think the last thing that I want to remind you or kind of point out to you that's a little bit weird here is these last two ions have 2 rows of exceptions. Because we have all of these normal exceptions that every other insoluble thing has, then hydroxide and sulfur also have calcium, strontium, and barium that are exceptions, things that can make them soluble. So don't forget those bottom 2 ions to read all the way to the end of that line and to look at the next one. So that's our chart. I'm going to do the first row of examples from our page 8, but I'm going to do them here with my chart visible so that you can kind of see the process of how to use the chart and not just trust me that it's in the soluble or insoluble area. So to start things off, we have NaCl. Remember that we're going to start by looking at the end of our compound, the last ion or element. Find that in our leftmost column of ions, and it just so happens to be in the soluble section. And I have to check, is Na one of its exceptions? No, it is not. So because it's not, I'm not going to get pulled over into the insoluble area, which means that I am just going to be soluble. So NaCl is soluble because chlorine is soluble and Na is not an exception to that rule. Now in our next example, we have AgCl. So if I'm still and always starting by looking at the element at the end, then I'm still coming back down here looking at our Cl rule. And just like in NaCl, Cl wants to be soluble, but we always have to check the beginning element. This time we start with Ag, and I do see Ag on the list of exceptions for chlorine, which means that our whole compound is going to be insoluble because of our silver. Chlorine wanted to be soluble, but that silver forced it to be insoluble. And that's really all there is to it. We're going to do a couple more examples. Next is Na3PO4. I know it's a big complicated looking formula, but I'm still just going to start from the end and try and find that PO4 chunk in my list. And this time it's down in our insoluble area. So it might be insoluble, but if I check, do I see Na listed out over here? And while I don't see it right here, I do notice that my alkali metal cations, which are being sneaky by not listing them all out, it does have Na in there. So that alkali metal, that Na, is going to force my phosphate to be soluble. That whole compound will dissolve in water thanks to that alkali metal, that Na. So this is basically what I want you to do, and in class we basically took this time now individually to try out these problems. We filled in that this top row is soluble, insoluble, and then soluble, hopefully. Those are those problems I was just talking you through there. And yes, I do recognize that NH4OH is a repeat on here, but hopefully when you do it, you get the same answer both times and you agree with yourself. But go ahead and try these out and come to class and make sure to double check these with me or one of your other classmates to make sure you're on track, because it really should just be kind of reading one more type of chart and graph and just getting familiar with it. But it's easy to make little mistakes if we're not familiar with it, if we're not doing it. So let me know how I can help you figure this stuff out, but hopefully it's not too bad. And if you happen to have time, not something that was assigned or stamped during class, you didn't really miss out on this, but in our next class, we're going to be doing a lot of stuff, trying to get a lab done and turned in, and I will be stamping worksheet 10C. And so you could get a little bit of a head start by completing this first part and circling compounds that will not dissolve in water. And so if you want to give that a try, if you're feeling confident with this chart stuff, you should have 7 circles in this section if we've done it correctly. And once again, I'll help you check your work and make sure you understand the stuff next time in class, but that could be worth your time if you do have it. So